Good evening, everybody. I'd like to welcome you all on behalf of NYU Abu Dhabi, and thanks very much for coming despite the weather tonight. It's my pleasure to introduce Rob Fender, who's Professor of Astrophysics at the University of Oxford. Rob is going to tell us about black holes, and black holes are very peculiar objects. They're some of the most compact or dense objects in the universe, where extremely strong gravity sucks in matter that plunges into the black hole. And yet, black hole accretion, this process of matter getting sucked in, is actually capable of producing accelerating matter away from the black hole as well. And Rob's been at the forefront of this research for the last couple of decades. So Rob's work has shown that these jets are the fastest matter moving in our galaxy. Rob studied at the University of Southampton, the Open University, and the University of Sussex in England, before being awarded a fellowship at the University of Amsterdam in the Netherlands, where he then became senior lecturer. It was in Amsterdam where Rob led his group to many discoveries related to black holes and similar objects. He found that black holes suck in and eject matter and accelerate them to close to the speed of light. Rob also found that radio waves from jets coming from black hole accretion are extremely common. So a lot of black holes are out there in our galaxy and other galaxies that are accelerating matter away from the black holes as well as sucking matter in. Rob's work has also, for example, helped us to understand how many black holes there are in our galaxy and inferred others as well. After Amsterdam, Rob moved to the University of Southampton, where he became Professor of Physics and Head of Astronomy. He became more involved with radio transient searches and helped the development of networks of new radio telescopes that were going to detect the signatures of thousands of black holes in the universe. He was leading the LOFAR UK group, which is a low-frequency network of radio telescopes based mostly in the Netherlands and over Europe. And finally, in October 2013, he moved to the University of Oxford, where he is currently Professor of Astrophysics, and he's also a visiting SKA Professor at the University of Cape Town in South Africa. SKA is the Square Kilometre Array, which is going to be the largest groundbreaking network of radio telescopes that we've ever built on the Earth. So without further ado, please give a warm welcome to Professor Rob Fender.
Thank you very much, Dave. I do apologise for bringing the weather from England with me. I gather that this is not at all typical weather for Abu Dhabi, but that's all I've seen, so maybe that's not true. Okay, so what I'd like to do is spend the next, the next 45 minutes or so telling you something about black holes. Black holes are just about the most exotic predictions of all the different flavors of theories of gravity that we've had over the last few hundred years. And yet, as far as we can tell, based upon all the observations we've made of the universe, they are real, they are out there, and they are at the heart of some of the most exotic phenomena we see in the universe. Not only that, but at their centers, which remain tantalizingly unreachable, will be the secret, the key to understanding new physics. We know that our current theories of physics break down at the centers of black holes, and yet, at least at the moment, these centers, these singularities are shrouded from us. They're cut off from our half of the universe by the event horizons of the black holes. So I'm going to give you a tour of the next 45 minutes of some of our understanding of black holes and how they interact with other objects in the universe. Now, 233 years ago, the Reverend John Mitchell was the first person to propose the existence of black holes. Here is the abstract of the paper, which was published in November 1783. And John Mitchell was living in a time when Newton's theory of gravity was the prevailing theory, and in Newton's view of gravity, light was made up of tiny little particles. There was a corpuscular theory of light, and therefore you could imagine that light could be affected by gravity. And on the other hand, people had just started measuring the speed of light. And it was realized that if you increased the mass of an object then the escape velocity from the surface of that object would increase. And John Mitchell was the first person to actually think, well, if I keep increasing the mass of an object, at some point the escape velocity from the surface of that object will reach the speed of light, and nothing will ever be able to escape from that object. And he envisaged stars of about 500 times the mass of our own sun, from which you could launch little corpuscles of light, which would then actually turn around and fall back to the surface of the star, much like you would get if you launched something up from the surface of the Earth, which didn't have the escape velocity of the Earth, from the Earth. The writings of John Mitchell were, in fact, pretty much forgotten and lost until the 1970s, by which time a completely new view of black holes had emerged based upon general relativity, but it does look like his work was the very earliest work to consider the possibility that objects such as black holes may exist in the universe. The history of the way that people think about black holes it's a very interesting history, and I don't think I have time during this talk to really run through all of it with you, but here's just some highlights. So 1783, 233 years ago, was this seminal work by the Reverend John Mitchell. However, one of the reasons that this work was discarded and forgotten was that in the 1800s, James Clerk Maxwell and others showed that light was best described by an electromagnetic theory where light was a wave. And of course, it seemed completely implausible at that time that waves moving through some kind of ether could be affected by gravity. So the idea that light could be bent by gravity was almost entirely dismissed as being absurd. And anybody who could remember Mitchell's work would have dismissed it as completely incorrect. However, about 100 years ago now, Einstein, of course, came up with general relativity, which we've been celebrating for the last couple of decades now. And in general relativity, it was very rapidly realized that it was entirely possible that there could be objects such as black holes. And I will describe in a moment what those objects could be. And one of the most poignant stories is that a thing called the Schwarzschild metric, which describes exactly how space and time behave around a non-rotating black hole, and which is entirely appropriate for many of the astrophysical black holes we see in the universe today, was developed by Carl Schwarzschild actually whilst he was in the trenches in World War I. So this was a scientist who had been sent to the trenches to fight. Whilst at the trenches, he worked out from Einstein's newly published theory that had only been published a year before that there was a particular solution which basically corresponded to the orbits around one of these general relativistic black holes. Shortly after sending in his paper, he was killed at the front. There were lots of further developments, but I'll highlight a couple more. In the 1960s, Roy Kerr and Ezra Newman calculated the metrics for rotating and charged black holes. And one of the incredible things about black holes, even though they can have 1 billion times the mass of the sun, is that they can be entirely described by just 3 numbers. They can be described by their mass, their spin, their rotation, and their electric charge. So the descriptions provided by Kerr and Newman basically completed the set of the 3 parameters, and that is it. That is all that you need, at least in general relativity, to describe the properties of space and time around a black hole. And this is entirely this is absolutely remarkable. As I say, you can have something that has 1 billion times the mass of the sun entirely described by just 3 numbers. So if you think about it, that's an enormous loss of information of the things that went into creating the black hole. Famously, in 1967, John Wheeler coined the phrase black hole for the first term. So previously, people had referred to things as like dark stars, for example. The phrase was a little bit controversial, particularly amongst the French at first, but has now become generally accepted as the nomenclature for the objects which we study. And then I will end my very brief history of people considering black holes. In 1990, when Stephen Hawking famously conceded a bet that he had made with Kip Thorne that a particular binary star system called Cygnus X1 contained a black hole. And it's worth showing you this bet. So this is Kip Thorne, who appears at the end of my talk later on in the story of black holes. And here, of course, is Stephen Hawking. And they made this bet here in 1974, and the bet was conceded in 1990. And the bet reads, whereas Stephen Hawking has such a large investment in general relativity and black holes and desires an insurance policy, and whereas Kip Thorne likes to live dangerously without an insurance policy, Therefore, it be resolved that Stephen Hawking bets 1 year subscription to Penthouse as against Kip Thorne's wager of a 4-year subscription to Private Eye that Cygnus X1 does not contain a black hole of mass above the Chandrasekhar limit. The Chandrasekhar limit here basically is a mass of a few solar masses, which means it's the kind of black holes that we envisage in general relativity. So Kip Thorne was a bit of a naughtier character than Stephen Hawking, and Stephen Hawking conceded the bet in 1990 and paid up the 1 year subscription of Penthouse to Kip Thorne because, in his view, the evidence had become overwhelming that in some particular binary systems, the objects that we saw in these systems were black holes. Later on in the talk, I will show you the evidence for a black hole at the center of our own galaxy, but for now, please just take it as read from me that the evidence that there are stellar mass black holes out there in binary systems is more or less overwhelming. What is one of these black holes? Well, a black hole is a region of space, as I've already intimated from the earliest theories, from which no signal at all can escape. So within general relativity, mass curves space and time, and beyond a certain curvature, the velocity required to get out of that dip in space-time would exceed the velocity of light. However, the black holes that we understand to exist in general relativity are not the dark stars with a surface that John Mitchell first envisaged. In our current theories of gravity, we believe that if you crush something to a density such that it will become a black hole, then nothing can stop the collapse of that matter to a single point at the center, which we refer to as a singularity. So once you take an object and compress it to a size at which it will become a black hole, the matter inside it will continue collapsing eternally to a point at the center where the densities will reach infinity. This point at the center we refer to, excuse me, as the singularity, and at the singularity we know that general relativity, which predicts the black holes, which we see, cannot be a complete description of nature. General relativity is what we call a classical theory, therefore that allows distances to go down to zero, and it basically has divide by zero in it, which of course makes no sense at the center of the black hole. Okay. So we know that the center of the black hole is what we need to understand to make the next steps forward in physics, perhaps towards something like quantum gravity. But we can't see it because the black hole is cut off from us by this event horizon, which is the region at which you need to be traveling at the speed of light to escape from the black hole. So we have this frustration that the new physics lies here, but it's cut off from us forever by the event horizon. But it's important to realize that the event horizon is not solid. Inside the event horizon, it's entirely empty. It's just curvature down of space-time to the center point called the singularity. Okay, so black holes come in two different flavors. Black holes are observed in the universe to come in two different flavors, and I want to tell you a little bit briefly about those two different flavors. So what we call stellar mass black holes are black holes that have masses which are comparable to the masses we measure for the stars you see at night when you look out at the universe. So these typically have masses about 5 to 20 times the mass of our own sun. And we believe we understand the route to which these black holes can be created. We believe that if you have a very massive star, at the end of its life it can collapse. There will be a supernova explosion, and it is entirely plausible, and we think we understand the physics, that a black hole of maybe 5 to 20 solar masses can be created. These black holes are very small. So a 10 solar mass black hole, so a black hole which has 10 times the mass of our own sun, is just 30 kilometers across. And there's a very simple scaling between the masses of the black holes and their size. So however many solar masses the black hole weighs, then its radius is 3 kilometers times that number. And just to throw in another historical note, the general relativistic treatment of the collapse of a massive star down to a black hole was in fact first performed by Oppenheimer and Schneider, and this is the same Robert Oppenheimer, of course, who famously went on to become part of the Los Alamos atomic bomb project in the USA afterwards. Sometimes these stellar mass black holes are observed as bright X-ray sources in the sky, and these allow us to identify sites in the sky where there are such black holes and study them further. So the routes to black holes, the routes of stellar evolution, as we call it, the path from the birth to the death of the stars, follow two distinct tracks, depending on whether or not the stars are low mass or high mass. So here is the path which corresponds to the likely trajectory of our own sun through its lifetime. So we believe that all stars start off as clouds of gas and dust between the stars that for some reason are perturbed and start collapsing under the force of gravity until they become so dense that fusion starts in their cores and we can call them stars. They then spend a very, very long time stably burning, so a period that can be many billions of years. And our sun is currently at this point in its stellar evolution. At some point, fusion will start to occur more and more in the outer layers of the star and will have ceased in the center of the star, such that the outer layers become very hot and expand, blow off, and produce spectacular nebulae, such as the one you see here, which we call planetary nebulae. These nebulae are called planetary nebulae for historical reasons. When people first saw them through telescopes, they looked like disks, so people thought they might be planets. In fact, they're very, very distant clouds of gas and dust that surround old, low-mass stars. And what will be left at the center of this planetary nebula will be a white dwarf. And that's the ultimate trajectory of our sun. Our sun will get from here to here in about another 4 to 5 billion years. So there's nothing to worry about right now. However, high-mass stars behave in a very different way. So high-mass stars, although they have more fuel, they burn that fuel very, very much faster than the low-mass stars. So the trajectory for a high-mass star is that it also goes through a stable period of burning, but instead of being several billion years, the stable period of burning could be as short as maybe only 10 million years for such a high-mass star. The high-mass star will become a red supergiant rather than just a red giant, such as our own sun will become. And the core of that red supergiant will collapse at some point into a supernova explosion. And what has happened here is that there has been burning at the center of the star, which has burned the elements progressively up until you get to iron. And then the temperature and pressure increase once more, and you start to combine iron together. But when iron is combined together, it doesn't release any more energy. There is nothing to stop the gravity. The center of the star collapses. You get a rebound, you get an explosion, and this is what we call a supernova. And the end products of supernovae can be either things called neutron stars, which are the last stop before black holes. They are the final stable objects with surfaces we know of in the universe, or if you compress a little bit more, then you end up as a black hole. So every supernova explosion produces a black hole or a neutron star. So how frequent are these supernova explosions? So what I'm showing you here is a movie that started in about 1905, which goes up to about 2 years ago, where this is a projection of what the sky looks like, the entire galaxy looks like through an optical telescope. Okay, so we've just left it fixed there as a background to give you some idea. So here's the center of the galaxy, here's the galactic plane, the Milky Way. Every time you see a flash, it's a supernova going off in the sky. Okay? And what you will notice is that particularly after World War II, the rate of flashes in the sky is increasing very dramatically. Now, this does not mean that the rate at which stars in the universe were exploding increased dramatically after World War II, but in fact is, of course, because we started surveying the sky more and more frequently with big telescopes to look for supernovae. So every single one of these flashes, as I say, is an actual discovered supernova. And we started doing very systematic surveys for supernovae. So in a moment, you'll start seeing patterns emerge in these discoveries. So you now can see, sometimes you see tracks where people have been observing dedicatedly with certain telescopes just looking for supernovae. So we know that the rate of supernovae in the universe is very, very large, and that every single one of these produces either a black hole or a neutron star. Incidentally, the last supernova within our own galaxy was the one that was observed by Kepler back in 1604, and yet we think that the rate of supernovae within our galaxy should be about 1 every 100 years. So we are well overdue for a supernova within our own galaxy, which should be an exciting event, hopefully not too exciting. Okay, so how do we see black holes? Well, we see them via accretion, which is something that Dave touched on in his introduction, which is that if a black hole gets near to a lot of mass, that mass will start to fall down towards the black hole, and ultimately most of that mass will fall into the black hole across the event horizon and will add to the mass of the black hole. However, usually, as mass falls down towards the black hole, it has a little bit of something we call angular momentum, which means it first swings around the black hole, and then it will intersect the stream of matter that's falling in, and a disk will flatten out and form around the black hole, and this disk will slowly feed matter into the black hole. So this is something we call an accretion disk, and these accretion disks can get very, very bright, and they can tell us where black holes are in the sky. So most of the stellar mass black holes which are produced by supernova explosions actually are sitting out there, floating in space between the stars on their own. They're not accreting very much matter, they're not glowing very, very brightly, and they are more or less invisible to our modern technology, our modern instruments. In fact, it's probable that the nearest black hole to the Earth is only a few times further away than the nearest stars that we know to the Earth. So the nearest star we know to the Earth is the Alpha Proxima Centauri system, which is about 4 light years away, and it's probable that within about 10 or 20 light years, which is very small on the cosmic distance scale, there is a stellar mass black hole floating somewhere in space, which we're not able to see. However, sometimes these black holes end up in binary systems with other stars, and they are able to accrete large rates of matter from these binary stars. They become very, very bright, and these are systems called X-ray binaries, which are able to study intensively and understand black hole accretion and feedback. So this is, of course, an artist's impression of such a system, but this is not just a random artist sketch. This is actually a proper simulation of what such a system would look like by a proper scientist, where there would be a 7 solar mass black hole here at the center of the accretion disk, in orbit with a half solar mass normal star in about a 1-day orbit. And those are typical parameters for such systems. So the black hole is slowly consuming the companion star. Matter is coming off the companion star, spiraling down towards the black hole, and this accretion disk is formed, which is very, very bright. Sometimes we observe a phenomenon which no one had predicted theoretically, and yet which we find to be entirely ubiquitous when it comes to black hole accretion in the universe, and that is a phenomenon known as the jet, which is a very, very narrow, collimated, powerful outflow of matter and energy that comes from very, very close to the black hole. No one predicted these, and yet they were everywhere. They are everywhere in the universe. So what I'm showing you here, these are real data of very high resolution, very high angular resolution, so very fine detail, observations of a black hole binary system which sits at radio wavelength, so with radio telescopes, where the system sits about here. And the blobs that you can see are actual blobs of matter. So they've been typically estimated to be something like several times the mass of Everest, each blob, and they are moving away from the central source at 26% of the speed of light. So that's an enormous amount of energy. This particular source has the interesting name SS433, and this source is always doing this. If you take an observation on any day, you will see these blobs of matter firing away from this jet. You can also see some very interesting phenomena, which is that the angle at which the stuff is moving away from the central source is actually rotating slowly. And by studying this source over many years, we found that it has 162 days. So these jets are firing away from the source, and they're actually precessing with a period of about 162 days. The power in these jets is something like 100,000 times the total power output from our own sun. These jets are not just a small isolated phenomenon close to the stellar mass black hole, but in fact they propagate out and then they interact with the gas and the dust that's around the black hole, and they deposit their energy in the surrounding, what we call the surrounding interstellar medium, in the case of objects within our own galaxy. So what I show here is the same movie of the jet that I showed in the previous slide, but expanded by about a factor of several thousand. And what I show around it is a wide field radio image of our galaxy in the local environment of that source. And actually what we see is that these jets, over probably something like 10 or 20,000 years, have distorted an enormous bubble in the interstellar medium, deposited a huge amount of energy there. This is not a small thing on the sky. I mean, obviously the moon is not really there. This is there to give you an idea of the angular scale of this phenomenon. Were you able to see the sky with radio eyes, you would actually see a shape on the sky produced by these jets that is several times the size of the full moon. And I will return to these jets shortly in the context of much larger black holes. So there is another variety of black holes, which are the so-called supermassive black holes. And these are black holes which have masses somewhere between 10,000 and 10 billion times the mass of our own sun. They almost certainly exist at the centers of most galaxies, including our own galaxy. And I will show you at the end of this talk some of the beautiful data which corresponds to the black hole at the center of our own galaxy. We're certain that they're out there, but we don't really know how they're formed. We have a very clear understanding of how these stellar mass black holes might be formed in these supernova explosions, but we don't really know how you form these supermassive black holes. The most plausible route really is that you create a stellar mass black hole, and just over billions of years it accretes so much matter and it merges with other black holes, and it basically just grows over billions of years. So probably one of the very earliest observations of evidence for a supermassive black hole was made 98 years ago. So Heber Curtis was the director, I think, of the Lick Observatory in California in the USA, and he observed a nebula in the sky which went by the name M87. So this was the 87th object in Messier's catalogue of nebulae in the sky, and no one knew what these things were at the time. And what he wrote down in his notebook, and he was just looking through the eyepiece of the telescope, what he wrote down in his notebook was that he could see a curious straight ray which was connected with the nucleus of this galaxy. Now, this is, of course, not an image from his telescope, but it's probably vaguely comparable quality. And what you see here is this is an enormous galaxy. This is a giant spherical galaxy which has several times the mass of our entire own galaxy. And there's this little ray of light coming out from the center of the galaxy, which appears to go in a straight line. We now know that this ray of light is actually one of these jets carrying an enormous amount of energy, mass, and power away from a central supermassive black hole in the M87 system. And again, this phenomena is better revealed by observations at radio wavelengths. So, if we make, here's the optical image again, and remember there was a tiny, you probably can't see it now, but there was a tiny little optical line coming out here. If we make observations on about the same scale with radio telescopes, and we see that the optical line is actually beautifully reproduced in radio emission, and we can see evidence that the radio emission, which is this jet of material, is flowing away from the central black hole, and at a distance of perhaps 10 kiloparsecs, that's almost as big as our entire galaxy, starts to become diffuse and is interacting with the surrounding medium. Interestingly, we don't see the jet on the other side, which is probably not because the jet is one-sided, but probably in fact because this jet is moving very close to the speed of light. If we look on much larger scales with radio telescopes at lower frequencies, this radio emission you see here now is entirely contained in the red stuff there, and all of the yellow stuff is diffuse radio emission, which is evidence that this phenomenon has been going on for at least hundreds of millions of years, depositing huge amounts of energy into the surrounding environment, and this is energy which we can trace all the way back to the central black hole in the system. And in fact, a couple of years ago, spectacular observations were made again with the very highest angular resolutions with radio telescopes of the black hole at the center of this system. So if I take this radio image, which you saw in the previous slide, and zoom in by about a factor of 1 billion, then you can see these radio images, and these are the highest resolution images ever made of this black hole. And what you can, I think what you can just about see is that you see matter and energy are flowing away in this direction from the central black hole. The angular resolution of these images is only about 50 times the size of the event horizon that we estimate for this very, very massive black hole in the system. So we're almost at the point at which we can actually directly image the event horizon from the system. But we see that the black hole itself can start from a very, very small scale and can send energy and matter out to scales that are tens of billions larger than the black hole itself. Now, incredibly, we now realize that this feedback, such jets from supermassive black holes, actually acts to regulate and throttle the growth of the most massive galaxies. It's been a mystery for several years for those people who work on the evolution and growth of galaxies, why galaxies don't grow larger than the largest galaxies which we see. Okay, there's so much matter out there and there's so much time for galaxies to accumulate matter that they really should grow very much larger than the largest ones we see. And what we believe is now happening is that these jets, as they fire away from central supermassive black holes, put so much energy into the surrounding gas that that gas remains agitated and hot and is never able to condense down onto the galaxies. So instead of forming very large galaxies, what we end up with is considerably smaller galaxies which are surrounded by a cocoon of hot gas which has been made energetic by the transport of energy from the central black hole. And this is a very, very big discovery which very much changed people's ideas of galaxy evolution. However, the jets from these black holes, these supermassive black holes, tend to evolve, tend to change dramatically on timescales no shorter probably than thousands or millions of years, which gives us a real problem in understanding the detailed physics of how they operate. So how do we solve this problem? Well, we solve this problem by returning to the stellar mass black holes in the binary systems. And there's a very neat trick that we're able to use. Essentially, all processes close to black holes, the timescale for those processes scale with the mass of the black hole. And what this means is that if you compare a black hole in a binary system, which maybe has 10 solar masses, with a black hole with the supermassive black hole at the center of M87, which we think has 10 billion solar masses, then if we observe one of these stellar mass black holes for about 1 year, in many senses, which are actually quite reasonable, what we're studying is about 100 million years in the evolution of a supermassive black hole. So what myself and many others, I should say, this is of course not by a long way, not just my own work, but what myself and others, including 2 people in this room, have worked on considerably over the last few decades is understanding in detail how accretion is related to jet formation in black holes and seeing whether or not that is applicable from the X-ray binaries, the stellar mass black holes, to the supermassive black holes. So what you're going to see in the next slide is the first 10 seconds of a movie, and this is a movie which encompasses an entire year of real data taken by an X-ray satellite monitoring the behavior of a black hole within our own galaxy. So the movie will play through for the first 10 seconds, and then I'll explain what you're seeing. So what you're seeing in this movie is, and you should focus on the top panel, these are real X-ray observations taken by an orbiting satellite called the Rossi X-ray Timing Explorer, which unfortunately was crashed into the ocean a few years ago in order to, presumably, to save money. And what you see in this top part of the diagram is that basically the y-axis, so up and down, represents how bright the source is, how many X-rays it's producing. And the x-axis tells us something about actually what is the temperature and spectrum of the accretion flow. And what you really need to understand is that when you see data over here, it means you have a full accretion disk that is extending all the way down to the black hole. Okay. The lower panel actually tells you about how much variability you're seeing from the black hole. And this is a very important diagnostic of black hole physics because things vary very rapidly close to the black hole event horizon. But I will not use these data in what I describe next. The color of the dot tells you something about how powerful and in what form the jets from this black hole are at the time of these observations. So when the dot is blue or green, then it means that there is a powerful jet coming from this source. And I should say that this movie is scaled such that 1 second is 1 week. and you're observing 1 year in the life of this source. So what you've observed is the first 10 weeks of the evolution of this source as it went through what we call a bright outburst. So we look at these data and we make detailed analyses of X-ray, radio and optical data, and we try to understand them. And the picture that we end up with is that when the source is on the right-hand side of the diagram, it's in a state where, for reasons we don't really understand, the accretion disk doesn't make it all the way down to the black hole, but there are very powerful jets. And in this mode, most of the available energy, all this energy that can be liberated by black holes accreting, is actually going into these jets and is firing away into the surrounding medium. So this is a good mode for this kind of feedback from supermassive black holes, which might help throttle galaxy growth. I'm now going to show you the movie again, but the first 20 seconds. So this is when the jet is on, but then something dramatic happens for the next 10 weeks. The source moves horizontally in the diagram without getting any brighter. And for reasons we don't understand, this means that the accretion disk, without the source becoming more luminous, the accretion disk actually filled in all the way to the black hole. This bright yellow star here indicates the point at which we saw the strongest and most powerful relativistic jet ejections from this source. So this jet was getting more and more powerful, and then at some point we saw a peak of this emission. And what we think is happening during these phases is that actually as the source is getting brighter, it is oscillating between states which produce a jet and the accretion disk doesn't make it to the black hole, and states in which the accretion disk makes it all the way down to the black hole, but the jet is switched off. And we don't know why the jet switches off when the accretion disk comes all the way down, but we know by making observations, we know empirically that it does. So that's the first 20 seconds of the movie. I'll now run the entire movie. So this is the entire year of behavior of this source. So the jet is on, the source becomes erratic and unstable and produces a very powerful jet here. We then see that for most of the rest of the outburst, the source stays over in a region in which this accretion disk comes all the way down to the black hole. And this is the state in which these powerful jets are not present. So when black holes are in this state, this feedback, this action from a supermassive black hole, which might have helped throttle and regulate the growth of the galaxy, is not occurring. Now the source slowly starts to become less luminous. It slowly starts to become less bright over time. And then suddenly, towards the end of the year, the source transit back across to this side of the diagram. Blue. It went blue there, you noticed, and then it fades back down that line. And the fact that it went blue indicates that our other observations indicate that the jet switched back on. Now, this is a sort of phenomenological picture of black hole accretion, which I can summarize in this slide. So when the sources are on the right-hand side of the diagram, we have this powerful jet. When they're transiting, they're unstable. But for most of the rest of the outburst, this disk comes all the way down, and they're very bright, but they're not producing the feedback in this jet. What we now understand from studying many tens of outbursts of stellar mass black holes is that this behavior is ubiquitous. Black holes always behave like this. This is a universal pattern of behavior which black holes follow. We don't understand the underlying physics, but we know that this is what black holes do. In parallel, or following this work, people have studied as best as possible populations of supermassive black holes and have come to the remarkable conclusion that the same patterns apply to supermassive black holes. Now, we very rarely see these supermassive black holes varying, but we can look at large populations of objects. We can look at how the accretion disk seems to be compared to how the jet seems to be, and we draw the conclusion that pretty much everything we've learned from studying the stellar mass black holes is also applicable to the supermassive black holes. And therefore, by studying these stellar mass black holes in these X-ray binaries, we're actually able to understand how feedback from supermassive black holes has helped to regulate the growth of galaxies on the largest scales over cosmic time. And this is a very important ingredient now in our understanding of galaxy formation, which really is one of the biggest questions in astrophysics today. Now, people are always very interested in whether or not we have a black hole, a supermassive black hole at the center of our own galaxy. So for the last part of the talk, almost the last part of the talk, I'd like to tell you something about the supermassive black hole at the center of our own galaxy. So there is a supermassive black hole at the center of our own galaxy, and we give it the name Sagittarius A Star. And we give it that name simply because it is a bright source in the direction of the constellation Sagittarius, which is the constellation which happens to contain the center of our galaxy. And A star means it was a particularly bright and interesting radio source. So we believe that pretty much all galaxies, all massive galaxies now, we believe, contain supermassive black holes at their hearts. So what about our own galaxy? Well, yes, I've said Sagittarius A Star, we believe, is a supermassive black hole in our own galaxy. And our best estimates are that this supermassive black hole has a mass of 3 to 4 million times the mass of our own sun. So this is, of course, this is supermassive, but this is not as massive as the black hole in M87, for example, which we believed was something like 1,000 times more massive than this even. And I'm going to show you in a moment the observations which allow us to deduce this mass. But let me show you first off something about the center of our galaxy. The center of our galaxy is a very dense and interesting environment. This is an image in normal optical light, so that which you could see with your own eyes of the center of our galaxy. This image is about 1 arc minute across. 1 arc minute is the angular resolution of your eye. Okay, so the very finest detail you can see it at an angular size anytime with your own eye without using a microscope or telescope is 1 arc minute. So, you know, that's a pretty small patch on the sky. And this is what it looks like through an optical telescope. It turns out that it's a very dense region, and rather contrary to theoretical expectations, there's a lot of massive young stars in this region. If we look instead at infrared wavelengths and look at the cool gas in the center of our galaxy, then we see this. We see a twisted spiral of material. The center of our galaxy is around here. We see a twisted spiral of material, which indicates that there's a very strong gravitational field at the center of our galaxy, which is perhaps not surprising, and that there is dynamical interactions going on with the gas, and probably that's why there's lots of hot young stars there, because stars are actually being formed very close to the center of our galaxy. If we look at hot gas, which emits in X-rays, then the center of our galaxy looks like this. And in fact, when we look in X-rays, we see a lot of very hot gas. So this gas here is 10 million degrees centigrade. Okay, this is very, very hot gas. We see a large concentration of it near the center of our galaxy, and we see a point source towards the center of our galaxy, which we believe is the location of this supermassive black hole. And if I combine all of these different wavelengths together, then you see a very beautiful picture of the center of our galaxy, where you can very clearly see there's a high concentration of stars, there's lots of hot gas, and there's lots of cool gas, hot gas, and lots of stars. What we really want to do is look right down at the center of our galaxy, where probably there should be a supermassive black hole, and see if we can see direct evidence for it. Well, that requires very, very high angular resolution, which is very hard to achieve, and this is achieved using optical or near-infrared telescopes using a technique we call adaptive optics. So what you see here in the background, the blurred image is what a regular optical telescope could see. Even if it was a very big, powerful telescope with a 10-meter reflecting surface in it, it would still see the blurred image. But when you apply a technique called adaptive optics, when you compensate for the fluctuations in the light as it passes through the Earth's atmosphere, you can very much sharpen these images. And what you see in particular is this region here, right down close to where we think the black hole is, becomes very sharp, and you're able to see individual stars very, very close to the central black hole. So the movie I'm going to show you next is real data, and it's about 15 years of monitoring, of taking images at very high resolution of this region very close to the black hole at the center of our galaxy. And it's remarkable. It's one of the most amazing movies in astrophysics. So this is where we believe the center of our galaxy lies. The green and purple blobs, those are real stars. Those are images of real stars. They've been cleaned a little bit so you don't see any background noise, but those are real stars, images taken over several years, and they've been made into a movie. So what you see is that these stars, let's take this one for example, they start to move in an orbit. Now a star will only move because it's being affected by a gravitational field. This star moves in, it gets swung around very fast by something gravitating there, and then it goes back, and this particular object, we've actually seen complete an entire orbit around whatever the gravity source is at the center of our galaxy. And also these two other stars, 102 and 38. So you see, we're pretty good at taking the luminosity of a star and working out how much mass it's got. We've studied millions and millions of stars. So we know how heavy these stars are. And we can just apply Kepler's laws of orbits and work out what is the mass of the object at the center there. And we find that there is an object with a mass of about 3 million times the mass of our own sun lying right at the center of our own galaxy. It's unequivocal. There is no way you could hide 3 million solar masses of stars there, which is the other thing which could be producing such a gravitational field. It's possible to take these data and actually project over 100 years the orbits of stars around the center of our galaxy, which is what's been done in this movie, where every second that you watch the movie, 2 years has passed. And these, again, are based on real data. These are not artists' impressions. And what you see is that there are many stars which are orbiting around a gravitating mass at the center of our galaxy. As the movie zooms out towards its end, it rotates so that it corresponds to the viewpoint of the center of our galaxy, which we see from the Earth. And actually, we see that quite a lot of these stars exist in a flattened disk, which probably means they have some kind of common origin, much like the planets within our own solar system. And these are the stars which have unequivocally proved that there is a supermassive black hole at the center of our own galaxy. Okay, I think it's time for me to wrap up, but I think it's pretty obvious that I shouldn't wrap up without saying something about the recent spectacular detection of gravitational waves, which of course is very relevant to this talk. So, in September last year, a ground-based gravitational wave detection experiment called LIGO had been upgraded after 2 or 3 years of work from its initial incarnation as normal LIGO to advanced LIGO, and was due to open on the Friday of a particular week. And about a week beforehand, they switched this back on, and they were ramping it up to full sensitivity for the official inauguration and launch. 4 days before the official launch, they detected a huge signal in the detectors at this experiment. So I'm part of a network of astronomers around the world who receive alerts going, wow, there might be something gone off. Point your telescopes in this direction. The signal was extremely strong, and it seems unequivocally that they detected incredibly, days after turning the machine on, they detected the merger of 2 black holes, each with masses of about 30 times the mass of the sun, merging together over 1 billion light years away, producing a signal which we could detect in these detectors on the Earth. Here is Kip Thorne. Kip Thorne is one of 3 people who actually was a driving force for 30 years behind LIGO, and of course there's the guy who won the year's subscription to Penthouse from Stephen Hawking during that process. This is extraordinary. It's fantastic that we've detected, or they, I should say, have detected gravitational waves. No one expected that the first detected source would be merging black holes. People thought it was more likely that we'd see something else, like merging neutron stars. We're not even sure how you produce 30 solar mass black holes. You'll recall earlier that we expect the black holes produced in supernova explosions to go up to maybe 20 solar masses. So it's been absolutely fantastic. Here's the signals. The signals were as received by 2 different detectors. And what you see is that there's a gravitational wave signal being detected by the 2 detectors, and that over a brief period of time, a few milliseconds, the amplitude of the signal increased dramatically and the frequency of the signal increased dramatically. And what's happening there is that there are 2 black holes which have been orbiting each other for billions of years, slowly getting closer and closer together as they lose energy through gravitational waves. In the very last few moments, they start to lose energy through gravitational waves at an extremely high rate, such that the orbit collapses very, very quickly. And the signal you see is in the last few moments, the last few milliseconds, as the black holes spiral into each other, they're getting closer and closer together, which gives you an increasingly strong signal at higher and higher frequencies. The 230 solar mass black holes merged, and if you look at the mass of the resultant black hole, then it was about 3 solar masses short of what you would get if you added the masses together. And in fact, it looks like 3 entire solar masses worth of energy were annihilated and turned into gravitational waves in this event. This is absolutely spectacular. For a few milliseconds, this event outshone, in terms of power output, the entire rest of the visible universe. Well, there's a beautiful movie which goes along with this discovery. This is a real-ish simulation of the event. So this is what 2 black holes merging would look like if you were looking down on the binary as they merged. And what you're seeing is a background star field which is lensed. So remember, to go right back to the start of the talk, gravity in general relativity can bend light, and it is bending the light around the 2 black holes as they come together, and then as they merge to produce the single black hole. Absolutely extraordinary. There have been reports of journalists getting a little bit tired of the story after a day or so and saying, so what? I have a colleague who made the following statement, which I think is quite correct, which is that, we have detected gravitational waves for the first time. That's a Nobel Prize discovery. Not only that, but we detected gravitational waves from 2 merging black holes, which we never expected to see. It certainly is the first event. As he put it, what else did you expect? Mermaids? So I'm going to end by showing you this picture. This is the Hubble Ultra Deep Field. This is one of the deepest images of the universe ever made by mankind. These objects, when you first look at this image, they look like stars, but I think there's only 3 objects in this entire image which are actually stars. Everything else is a galaxy. It's a big galaxy like our own Milky Way or larger. When we make surveys like the Hubble Ultra Deep Field, we're able to estimate that there are something like 100 billion galaxies in the known universe. And we believe that pretty much all of these galaxies will contain at their centers supermassive black holes like the ones I've been describing. We also believe that in addition to the central black hole, most galaxies contain something like 100 million of these stellar mass black holes, the vast majority of which will just be drifting through space and will not be detectable. This means that whether or not you like it, there are out there in the universe something like 10,000 billion black holes just in the observable part of the universe. So they are certainly out there, and they're certainly at large. Thank you very much.
Hi, Professor. Thank you so much. Actually, very overwhelming. It seems that we know some stuff about the structure of the black holes, but do we know anything about the function? I mean, what's the significance of their presence in the universe? And if structure defines function,
yes.
I mean, is there a significance also of having a massive black hole in the center of each galaxy?
I wouldn't personally ascribe any willful significance to the existence of black holes. However, you ask what role they play, and I think it's clear that they play a very important role. So, traditionally, for many decades, and as portrayed in all the movies, they are just cosmic sinks into which everything falls, and ultimately, you might expect the universe to all have fallen into a black hole. But as we see, the black holes actually are acting to regulate the growth of the galaxies. So they are acting, these tiny, the size scale of these black holes is absolutely minuscule compared to the galaxies which host them, and yet they somehow manage to regulate the growth of the black holes. I can't give you a willful meaning for why they're there, but clearly they're a very important role they play in creating the structure that we see in the universe as it is.
Thank you very much for that talk. Again, it's very overwhelming to try to imagine, which the human mind cannot do, these astronomical, literally astronomical figures. Now, we are to suppose that there is When you talk of the universe and the amount of things that may exist within the universe, we must suppose that there is then a limit to the universe that we inhabit. So what I'm trying to do with my feeble mind, human mind, is trying to make, well, what, if there is a limit to our universe, what exists outside of this limit then? How can we say that there is such a thing as a limit to something which is supposedly infinite?
Yeah, well, I mean, that's a good question. So let me first off say that I think I say several times here. So we have here the statement, the known universe. What we know, what we think we know, is that the universe we see is limited by the telescopes that we have, and it will be forever limited because the universe is expanding such that parts of the universe will be forever beyond will not be observable. So probably there is a larger universe beyond a bubble which we can see. And we have to assume, but we can never prove it, that the rest of the universe behaves with the same physics that we see in our bubble. But again, it's actually very hard to prove that. We will never, unless something radically changes, we will, for example, like the universe turning around and starting to contract, which it clearly isn't doing at the moment, then we'll never be able to see this stuff and test that. But I think you asked a deeper question, which is that, we believe that the universe started something small as a big bang and is expanding, and what's it's expanding into and what's outside it. The cosmologists and theoreticians would tell you that the question is nonsensical and that all of space and time is contained within the universe, and all of space and time was contained within the singularity at the beginning of the Big Bang, and all of space and time is contained within the universe as we see it, and it doesn't make sense to ask the question to what it's expanding into. I mean, it's an unsatisfactory answer, right? I mean, I agree with you. It's an unsatisfactory answer if that's what you're thinking. But I mean, that as general relativity tries to inform us of what's going on, that is what we think is happening. It doesn't actually make sense to ask. Sorry.
I think in one of your slides you mentioned that you have you compare stellar mass black holes with supermassive black holes. Yeah?
Yes.
So that's basically an extrapolation you're doing based on some kind of observational data. So does that data give you any insights into the physics that might be possible, the new physics that you're looking for?
Well, so the way that we do it is that we, as you saw in the movie I showed, we can track the behavior of the stellar mass black holes. And this gives us this pattern that when you see an accretion disk in a certain way, the jet is either on or off. And we see when we look at a large ensemble of supermassive black holes, they appear to behave the same way. So that's why we can draw this conclusion. And it gives us some further clues towards the physics of accretion flows and the formation of these jets. My personal view, although it's not shared by all my colleagues, is that we are still a very long way from understanding how and why these jets are formed, but we are progressing in that direction. Does it give you a clue to the new physics at the center of the black holes? No, unfortunately not. Everything we see, all of these phenomena that we see are phenomena which are generated by processes which occur outside the event horizon in all our models. That's the only way we look at things. Well, perhaps we're being completely naive and stupid, and perhaps stuff is coming out from, and the event horizons are not there. But we believe we can explain everything we see from the flow of matter very close to the black hole, but not from inside the black hole. So we remain frustrated and tantalized by the fact that we know, there are 10 million billion cases out there in the universe, at least, where the clue to the new physics is, but it's hidden away from us by the event horizon. I don't know how we're going to get through that. Of course, for the supermassive black holes, if you were personally to cross the event horizon of a supermassive black hole, you would actually survive for about 8 minutes, right? So you wouldn't, if you were to go very close to a stellar mass black hole, you would be torn apart immediately. You'd be spaghettified, as people call it, which is you'd be pulled out very long and thin, and it would be bad for you. But if you were to cross the event horizon of a supermassive black hole, you actually probably wouldn't notice very much, except the sky would look different. And it may be that you could learn a little bit more about the physics that's happening at the center of the black hole, but you'd never be able to tell anyone else about it. So that's the problem.
Hi, thank you for that talk. Beyond the event horizon, so within the limits in which we can't see, it said that there is a singularity, a point of infinite density.
Yeah.
By definition of not being able to perceive this singularity, how do you arrive at that conclusion?
Well, I mean, the conclusion is almost certainly wrong. What I mean to say is that within our current understanding of physics, including general relativity, the last time that you can have a solid body which can stand against the forces of gravity is these things called neutron stars. And neutron stars are about twice the size of their corresponding event horizon. Okay, so if I took a neutron star and crushed it to about half its size, it would then collapse all the way to a black hole. So what I mean is that we know of no force which will stop gravity once you've gone past that point. So within the framework of general relativity, all the matter will end up at the center, which therefore leads to infinite density. It's clearly wrong, right? It's clear that it's wrong. There must be some other explanation. There must be some other physics going on at the center. But unfortunately, we can't see it. This is the problem.
I was wondering about the active phase. So when it goes from the accretion disk not reaching the center of the black hole
Yes.
to when it does, and
Yes.
obviously when it's not there, you have jets, and when it is to the center, there are jets. There's aren't. Sorry.
Yes.
Is there like a transition phase between them? How has it been observed how they get from one to the other? Is there a point where it collapses and then they appear? So is there a specific distance from the center at which point the jets appear? Or-
So there are ways of trying to track this behavior. So for example, you can look at the timescale of variability, and when you get closer to the black hole, it's smaller physical scales, things vary more rapidly. You can also look at how the spectrum changes. There's lots of ways of trying to investigate this problem, and it's a hot topic. This is something people want to understand. Not everybody agrees on the interpretation of the data. Okay, so I have to make this entirely clear. I have colleagues who would disagree with what I'm about to say. But it looks to me, and it looks to many of us, like the data actually strongly indicate the fact that you can track the accretion disk moving in. And you see the jet, actually, when the accretion disk is far out from the black hole, the jet appears to be quasi-steady. And as the accretion disk moves in, it appears to become more and more unstable. It's on-off, it's on-off. And then about the point where the accretion disk reaches in as far as it can, otherwise it would plummet into the black hole, the jet very briefly becomes extremely powerful and then is gone. So the accretion disk moves in, the jet is kind of powerful, but becomes more and more powerful, but erratic. And as it reaches the final point, the jet basically goes boom, and then is gone.